Hi dears, welcome to the second session of Introduction to Modern Physics. So already we studied electromagnetic waves, blackbody radiation, ultraviolet catastrophe, photoelectric effects, etc. In this session we will discuss wave-particle duality and de Broglie hypothesis and also Heisenberg's uncertainty principle. So light rays or energy electromagnetic radiations, they possess a dual nature. So already we in our classes we studied corpuscular theory or particle nature of light. That can be reflection of light can be explained as a particle nature. In a straight line, light will travel in a straight line. And also interference or diffraction. These phenomena of light are explained using wave nature of light. So light rays possess a dual nature. Depends on the problem, we will consider the wave nature or particle nature. So in a similar way, matter means electron, proton, atoms, molecules. This matter also should possess same dual nature. So matter is already have a particle nature and it behaves like wave under some conditions, or we can say moving particle have a wave nature. We call this wave as matter wave. So matter wave is the wave associated with the matter under some conditions. So de Broglie put forward a hypothesis that all material particles possess a dual wave-particle behavior. So in general, particle behavior is explained as momentum P and wave nature, or that's expressed as a wavelength lambda. So connecting these two, particle and wave nature, we have a relation. De Broglie proposed a relation lambda is equal to h by p, where lambda is purely a wave parameter and where p is purely a particle parameter. So this de Broglie relation that connects lambda and p. So lambda is equal to h by p, where h is the Planck constant, 6.6 into 10 raised to minus 34 joule second. Now let's discuss Heisenberg's uncertainty principle. So in classical mechanics, that deals the problems in macroscopic world. So in our usual system or usual world, that's our macroscopic world, the position and momentum of a body can be determined simultaneously with accuracy. We can measure both x and p simultaneously with 100% accuracy. But in quantum mechanics, if we deal with the microscopic domain, that means if we deal with the molecules or atoms or electrons, then we have to consider the quantum mechanics. So where the Heisenberg's principle of indeterminacy come forward. So the uncertainty principle states that it is impossible to measure the position and momentum of particles simultaneously with accuracy. It is impossible to measure both position and momentum of particles simultaneously with accuracy. We can measure the position and momentum simultaneously, but there should be some errors. With accuracy, we cannot measure. So for complementary variables, that's x and p. Suppose uncertainty in position is delta x and uncertainty is in momentum is delta p. Then the uncertainty relation Heisenberg principle gives delta x delta px is greater than or equal to h cross by 2, where h cross is h by 2 pi, where h is the Planck constant. H cross is h by 2 pi. So totally we can say delta x into delta px is greater than or equal to h cross by 2. In a similar way, that's for x and p. Here we have another variable, set of variable as energy and time. Suppose the uncertainty in energy is E, delta E, and uncertainty in time is delta t. Then uncertainty relation between E and T will be delta E into delta T is greater than or equal to h cross by 2.